The topic of my research is the interaction of the Indian craton with the Reunion plume. First of all, I'll give a brief introduction about cratons. They are the oldest lithosphere on this earth. If we see this global map, these blue colored regions are the approximate location of the cratons. One of the major characteristics of the cratons is that they have a very thick lithosphere. Normal lithosphere are around 100 kilometers thick, whereas these cratonic lithospheres are more than 200 kilometers thick. However, there is a controversy with the Indian craton thickness. If we see this lithosphere thickness map, we see that Indian craton is only 100 kilometers of thick, which is marked by this yellow or the green to yellow color. But this is not the only study that has suggested Indian lithosphere to be very thin. There has been a number of studies which have suggested different thickness of the Indian craton, and that varies from 100 to 260 kilometer depth. To address this discrepancy, many have suggested one hypothesis, that while the movement of the India, the Reunion plume erupted under the Indian craton at around 65 millions of years ago. And this event might have thinned down the Indian craton thickness. In this study, we want to test this hypothesis. To test this hypothesis, we developed the numerical model using a code that is CitcomS that can solve the convection equations in a 3D spherical domain. Apart from that, we use Gplex. It can give us the reconstructed geometry of the cratons. How it is done? Here we can see the present day locations of the craton, and if we see this animation, you can see that we can reconstruct back the cratons to its location at the distant past. Apart from just reconstructing the cratons, we can also find what was the surface velocity condition at that time. Gplex can do this up to 410 millions of years, but for this case we have reconstructed back only till 65 millions of years, which is sufficient for this study. So we develop our numerical models starting from this condition at 65 millions of years, where Indian craton is reconstructed back, is marked by this blue region, and the location of Reunion plume is given by this red region. We develop the forward models from the 65 to the present day and let the model run and evolve self-consistently. We change the different viscosity of the craton and the asthenosphere that I can discuss in the later part. Apart from the reconstruction of the craton, there is another parameter that will be very crucial for our study, that is the mantle plume. So this is our initial geometry of the plume that we have inserted in the location of the Reunion plume. The plume temperature is kept at 1600 degrees centigrade with a broad base and narrow tail and a thick head. Apart from its temperature control, we also incorporate the temperature dependent viscosity, which is given by this formula. Now eta 0 is the ambient layer viscosity, T0 and T are the non-dimensional reference and actual temperature, and E is the strength of temperature dependence. So how does it work? If E is equals to 0, then there is no temperature dependent viscosity. So even if the plume is there, but the temperature dependent viscosity will not be applicable. If we increase the value of E, then the temperature dependence will increase. So what does this temperature dependence means is that if we increase the value of E, then hotter temperature region will yield lower viscosity region, and the cold temperature region will translate a high viscosity region. So with this setup, we have developed number of models, and we will show one of the results from all these models. In this right panel, we can see that the snapshots are given from our models, where this black dashed line indicates the craton boundary and this blue dashed line indicates the 300 kilometer thickness marker. So initially our cratons were 300 kilometer thick, and as we evolve with the time, I'm showing the animation now, the plume starts to interact with the craton and it starts to erode the craton. And as we can see in this animation as well as in the snapshots, after 50 millions of years there is a significant thinning, and as we approach to the present day, around 50 to 60 kilometer craton has been eroded away. So we do our tests with different plume and the temperature dependent viscosity. For each viscosity combination of the craton and asthenosphere, we develop 4 different sets of model, where first is we do not incorporate any plume, second is we incorporate plume but the temperature dependence is turned off, that means the E is turned to 0, and then we gradually increase the value of E, that means we increase the temperature dependence, and we calculate how much aerial deformation has been experienced at different depths by the Indian craton. So let's take one example of this red line, which is a result from E is equals to 10 model. Here we see that at around 48 millions of years, this deformation reached to minus 100%. This means there is no craton existed at around 265 kilometer at 48 millions of years ago. That means this amount of craton has already been destroyed. And if we come to the next figure, we see that at around 28 or 29 millions of years ago, even the 240 kilometer depth reached to the minus 100% deformation. Whereas if there is no plume or if there is no temperature dependence, we do not see much deformation. So the deformation sticks to mostly near to the 0%. We'll show another case from a different viscosity combination where the asthenosphere is slightly decreased in its viscosity. This is 10 to the power 20 Pascal second, and we also reduce the craton root viscosity to 10 to the power 22 Pascal seconds, and we see that in this case the deformation is even more fast. So here, even if the temperature dependence is turned off, the craton is getting destroyed very quickly within 55 millions of years at 265 kilometer depth. At 192 kilometer depth, the craton is also getting completely destroyed at around 20 millions of years. So in this case, we see the craton can be thinned down more than 100 kilometers. So in conclusion, we say that Indian craton could have been thinned up to 50 to 100 kilometers due to the eruption of the Reunion plume, and this matches with the many seismic studies and the receiver function studies that suggests that Indian craton is not as thick as it should be.